Hi guys, welcome to our channel. Before we get started, make sure to hit that like button. Also subscribe to our channel, the fifth giant planet. So make sure to watch the full video. Strange things happened in our solar system when it was young and forming. During the later stages of solar system formation, massive protoplanets and planetesimals performed a chaotic gravitational ballet that caused many planetesimals to be rudely tossed into new and dangerous orbits by some of their dancing partners. This dangerous dance resulted in angular momentum exchange between planets and planetesimals, which caused migration, either outward or inward, of the unlucky baby planet. For example, the outward migration of the ice giant Neptune is believed to be responsible for the resonant capture of the ice dwarf planet Pluto and others of its frozen kind, termed Plutinos, into a 3.2 resonance with Neptune. In October 2015, a team of astrophysicists at the University of Toronto in Canada proposed that a close encounter of the worst kind with the enormous gas giant planet Jupiter that occurred about 4 billion years ago may have resulted in a long-lost giant planet's unceremonious eviction from our solar system into the space between stars. During this fierce and ancient chaos that resembled a kind of cosmic playground for kindergarten planets during recess, strange games were played by all of the young attendees. Planetary migration occurs when a planet or other body in orbit around a star, such as our own Sun, interacts with either a primordial disk of gas or playful planetesimals. This strange gravitational game results in the alteration of the young planetary body's orbital parameters, especially with its semi-major axis. In planetary systems beyond our own, planetary migration is thought to be the most likely explanation for the existence of roasting hot Jupiters. Hot Jupiters are exoplanets with hefty masses similar to our own solar system's behemoth Jupiter that hug their parent stars fast and close in searing hot orbits of only a few days. Most theories of planetary formation from a protoplanetary accretion disk of gas and dust whirling around a young star predict that hot Jupiters cannot form so close to their roasting, fiery, roiling stellar parent. This is because there is insufficient mass and the temperature is too high to permit the birth of rocky or icy planetesimals. It has also become obvious that terrestrial, rocky planets such as Earth may be subject to rapid inward migration if they are born while the gas disk is still lingering around its young star. The existence of a long-lost fifth gaseous giant planet in our Sun's family at the time of our solar system's formation about 4.56 billion years ago was first proposed in 2011. This missing fifth giant planet would represent an addition to the 4 giant gaseous planets that inhabit the outer regions of our solar system today: Jupiter, Saturn, Uranus, and Neptune. But if a missing fifth planet really did exist in our Sun's family long ago, how did it get kicked out? That is the question. For many years, planetary scientists have suspected that either Saturn or Jupiter was the culprit. But the new research, conducted by the University of Toronto astrophysicists, points a definite accusatory finger at Jupiter. Our evidence points to Jupiter, commented Ryan Cloutier in an October 2015 University of Toronto press release. Cloutier is a doctoral student in the University of Toronto's Department of Astronomy and Astrophysics and the lead author of a new study published in the Astrophysical Journal. The migration of the 4 outer gaseous planets is necessary in order to explain the properties and existence of our solar system's outer regions. In fact, our solar system does not come to an end beyond the blue-banded ice giant Neptune. Beyond Neptune, our solar system goes on and continues into the Kuiper belt, the scattered disk, and the Oort cloud. These 3 distant, frigid outer regions are believed to be sparsely populated by small icy bodies that are the source of comets. At their great distance from our star, accretion was much too sluggish to permit planets to be born before the solar nebula dispersed, and therefore the initial disk did not contain sufficient density to collect and form a planet. The Kuiper belt is situated between 30 and 55 astronomical units from our star, while the more distant scattered disk extends to more than 100 O. The extremely remote, frigid Oort cloud begins at about 50,000 O. 1 O is equal to the average distance between Earth and our Sun, which is about 93 million miles. However, the Kuiper belt was originally much closer to our Sun, as well as considerably more dense than it is now. It contained millions of sparkling, icy planetesimals, and it also sported an outer edge situated at approximately 30 O, which is the current distance of Neptune. After our solar system had formed, the orbits of all the giant planets continued to evolve, influenced by the way they interacted with the myriad of remnant, lingering planetesimals that still whirled their way around our Sun. After about 500 to 600 million years, about 4 billion years ago, Jupiter and Saturn evolved into a 2-to-1 orbital resonance. This means that Saturn circled our star once for every 2 Jupiter orbits. This resonance caused a gravitational push to develop against the quartet of giant, gaseous outer planets, causing Neptune to rampage past Uranus and crash through the dense planetesimal belt. The planets then scattered most of the small icy bodies inward towards our Sun, while they themselves traveled outward in the opposite direction, into the cold twilight of our solar system's outer limits. This process went on until the planetesimals finally interacted with the behemoth Jupiter. Jupiter's fierce and powerful gravity then shot the small icy bodies into highly elliptical orbits, or even evicted them from our solar system altogether. As a result, Jupiter traveled slightly inward towards our star. The duo of ice giant planets, Uranus and Neptune, the 2 most distant major planets from our star, are often thought to have migrated outward in this way from their original birthplace that was close to the orbits of the gas giant pair Jupiter and Saturn. Uranus and Neptune traveled outward to their current positions over the passage of hundreds of millions of years. At last, friction within the disk of planetesimals caused the orbits of Uranus and Neptune to become circular again. Strange things happened in our ancient solar system. Ice giants like Uranus and Neptune are primarily composed of relatively heavy elements such as sulfur, nitrogen, carbon, and oxygen. Uranus and Neptune both are made up of only about 20% hydrogen and helium in mass. This is in stark contrast to the duo of gas giants, Jupiter and Saturn, both of which are composed of 90% hydrogen and helium. However, the quantity of solid volatiles within Uranus and Neptune today is very small. Jupiter and Saturn are actually enormous balls of gas, and both of them may well contain only relatively small cores buried beneath their extremely heavy and thick atmospheres. In fact, it is sometimes thought that this pair of gaseous behemoths actually possess no solid cores at all, and they are actually composed entirely of atmosphere. Uranus and Neptune harbor larger icy rocky cores than Jupiter and Saturn, and relatively thinner atmospheres. The duo of ice giants are both enormous, but not nearly as huge as Jupiter and Saturn. Uranus and Neptune were probably not born where they are now, 19 and 30 from our Sun. This is because the accretionary process responsible for giving birth to the planets of our Sun's family worked much more sluggishly at greater distances from our star, where the ice giants are now. The protoplanetary accretion disk, composed of gas, dust, and ice, was far too thin in this distant region to permit planets of this enormous size to be born as quickly as they did in the toastier, brighter portions of the disk closer to the roiling fires of our star. Planetary scientists have a hard time explaining how Uranus and Neptune could have managed to grow to their huge sizes where they are situated today, because the protoplanetary accretion disk should have been destroyed before planets of this immense size had a chance to form in this region of our solar system. For this reason, many planetary scientists think that the cores of Uranus and Neptune formed closer to the young Sun, and only later traveled outward to their more distant, frigid home. Uranus has a weird orbit that is tilted far more than any other planet in our solar system. Some studies have suggested that this distant, greenish-blue giant world may have been mercilessly knocked over on its side as the result of a primordial collision with a world twice as big as Earth. Uranus is the larger of the ice giant pair and is the 7th planet from our Sun. Neptune, the 8th major planet from our star, is the smallest of the quartet of gaseous giant planets dwelling in the outer regions of our solar system. Neptune is a beautiful deep blue world, and it displays lovely and intriguing bands and stripes, as well as a fascinating spot that is actually a gigantic swirling storm akin to the vortices of hurricanes that wreak havoc on Earth. Neptune's enchanting stripes, spots, and bands are varying shades of beautiful blue, and this pretty blue hue is the result of atmospheric methane, not oxygen. However, some of Neptune's storms are fluffy and white and display a delectable marshmallow-like appearance. Neptune's large moon Triton may not have been born a moon at all. Pluto and Charon are inhabitants of the remote Kuiper belt, that reservoir for dancing cometary nuclei, and other icy objects and fragments and bits, some large, some small, all jitterbugging around our sun beyond Neptune's orbit. Triton is probably the strangest of all the 13 known moons of Neptune. Some theories suggest that Triton was evicted from its frigid home in the Kuiper belt and was doomed to wander lost and alone through interplanetary space. At long last, Triton traveled too close to Neptune's irresistible gravitational embrace and was adopted into the family of that planet. As Neptune pulled its adopted moon towards it, that icy and lost frozen wanderer from the distant Kuiper belt experienced a metamorphosis from a comet-like inhabitant of our solar system's frozen outermost region to a captured moon of one of the major planets. Triton now orbits Neptune, circling its adopted parent planet in the wrong direction. This backward orbit indicates that Triton is a captured object. Like all other moons, Triton is now a dependent of its parent planet, and it was given its name in honor of the demigod Triton's dependence on Neptune, the sea god of Greek mythology. The fifth giant planets are evicted due to a dangerously close planetary encounter. During such a catastrophic encounter, one of the colliding worlds speeds up so much that it breaks away from its gravitational bonds with our sun and escapes to freedom. However, previous research suggesting that giant planets could evict one another did not take into consideration the effect such violent encounters would exert on smaller, minor bodies, such as the known moons of the giant planets and their orbits. This is why Ryan Cloutier and his team turned their attention to planetary moons and orbits. The team of astrophysicists created supercomputer simulations based on the current trajectories of the moons Callisto and Iapetus. Callisto is a large Galilean moon of the planet Jupiter, and Iapetus is a mid-sized moon of the ringed planet Saturn. The team then went on to calculate the likelihood of each one producing its modern-day orbit in the event that its parent planet was responsible for booting out the hypothetical fifth giant planet, a catastrophe that would have resulted in a significant disruption to each moon's original orbit. Ultimately, we found that Jupiter is capable of ejecting the fifth giant planet while retaining a moon with the orbit of Callisto, Cloutier noted in the October 2015 University of Toronto press release. On the other hand, it would have been very difficult for Saturn to do so because Iapetus would have been excessively unsettled, resulting in an orbit that is difficult to reconcile with its current trajectory, Cloutier continued to explain. The study is reported in a paper titled "Could Jupiter or Saturn Have Ejected a Fifth Giant Planet?" published in the November 1, 2015 issue of the Astrophysical Journal. A cluster of icy bodies in the same region as Pluto could be proof that our early solar system was home to a fifth giant planet, according to new research. That planet may have bumped Neptune during its migration away from the Sun 4 billion years ago, causing the ice giant to jump into its current orbit and scattering a cluster of its satellites into the Kuiper belt in the outer solar system. The cluster, a grouping of about 1,000 icy rocks called the kernel, has long been a mystery to astronomers. The rocks stick close together and never veer from the same orbital plane as the planets, unlike the other icy bodies that inhabit the belt. Previous studies proposed that the tightly bound objects formed from violent collisions of larger parent bodies, but that hypothesis fell apart as soon as scientists realized these collisional families would have to be stretched across the Kuiper belt. But now, one scientist may have an answer for this Kuiper belt mystery. David Neswarny, an astronomer at the Southwest Research Institute in Boulder, Colorado, proposes the jumping Neptune theory in the September issue of the Astronomical Journal. Using computer simulations to trace the movements of the kernel back about 4 billion years, he found the objects had been swept up in Neptune's gravitational field as the planet migrated away from the Sun. Leaving its orbit near Saturn and Jupiter, Neptune pulled bits of the primordial solar system along with it as they rotated in tandem. The infant kernel traveled around the Sun twice for every trip that Neptune made. At approximately 4.2 billion kilometers from the Sun, close to its current position almost halfway to the outer edge of the modern-day Kuiper belt, Neptune's orbit lurched outward 7.5 million kilometers. The trapped objects couldn't keep up with the sudden change of pace, and they were jolted out of their orbital configuration 6.9 billion kilometers from the Sun, where they continue to travel today as the kernel. Neswarny says the only possible explanation for the sudden shift in orbit is that Neptune came under the gravitational sway of another object with a massive gravitational field, likely a giant planet. Uranus, Saturn, and Jupiter aren't candidates because their orbits have never interacted with Neptune's in the way that this proposed planets might have done. No one knows what became of the missing planet. But when Neswarny developed a previous model in 2011, he found that the best way to wind up with the present-day orbital configuration of the solar system was to include a fifth giant planet. The mystery giant was most likely ejected permanently from the solar system after disrupting the original orbits of the surviving planets. Nesvorny says, a casualty of its gravitational wrestling match. But back in 2011, he never thought he would find evidence of the planet's possible existence. The Kuiper belt is the clue, Nesvorny says. You see the structures there, and you try to figure out what kind of evolution would fit those structures. But trying to figure it out isn't so simple. Before landing on his current model of how the kernel could have formed, Nesvorny tested about 100 other possibilities. One of the most difficult parts of modeling, says astronomer J.J. Kevlars of the Dominion Astrophysical Observatory in Victoria, Canada, is to get multiple objects in the solar system to end up in the right place. Early models for the formation of Pluto, for example, put the dwarf planet in the correct location but neglected other parts of the solar system. What Nesvorny's models are doing is being very self-consistent and getting multiple structures right at once, which is really quite amazing, says Kevlars, who was not involved in the research. Nesvorny says the next step is to identify more objects in the Kuiper belt, particularly in the kernel. This could help scientists perform more precise comparisons that could improve the accuracy of the model. Nesvorny hopes observations from the Outer Solar System Origins survey later this summer will fill in some of the gaps. I'm very much looking forward to seeing what kind of observations they will have and how it fits the modeling, Nesvorny says. What do you think of our video? Let us know in the comments section below. If you enjoyed this video, make sure to hit that like button. Also remember to subscribe to our channel and enable notifications so you will be the first to know when we upload a new video. Thank you for watching.